Hi there. I'm really thankful to the organizers, like they're all my friends. So it's been for a while. So we are back again at Scale by the Bay. The topic is algebraic data types categorically. I'm a categorist more or less by education, but I'm a programmer. So when I encountered those algebraic data types, I started thinking, so what's that exactly? Why are they algebraic? And there was a lot of misconception about this and that. So about like last year, I eventually like put all those things together and well, and Uranus, so it didn't explode, but it exploded in my head. So I know now what it is, and I'll try to share with you my knowledge. So, but first, when we are in computer science, there's a lot of like kind of thinking, like in arguing, like, for example, I was teaching in Santa Clara University for 8 years. And when the students come over, they are like computer science students. I ask them, can you prove in piano arithmetic the commutativity of addition? Yes, for example, 2 plus 3 is 3 plus 2. And here's a proof, like I'm starting this. This is an expression for, I believe, number 3 and so on. And then I was patiently training them not to use proof by example. You can have a like counter example. That's a different story. So the same happens when you are trying to learn ADT, algebraic data types. Some people say abstract data types. Like you open a book, you open like a text and you see, for example, 2 plus 3 and then like a syntax tree and so on. So what is it? I don't know. So I was really curious about what is it about. So let me like walk over the things and explain to you what I understood. So first, the terms, notation, right? So if we have X and Y, a Cartesian, well, it could be types, it could be objects in a category, it could be sets in set theory. So a Cartesian product of them is like in sets, is just, it consists of pairs X, Y, where X is from X and Y is from Y. For example, a type X, Y, so it's a type of pairs in Scala. I'll be giving a lot of Scala example, although Scala is not like what I'm going to talk about. X to the power of n is a Cartesian product of X with itself n times. For example, array of X in Scala. So if you have arrays of the same size, so we have a Cartesian product of X with itself, the power of X. One is a special Cartesian product X to the power of 0. Is a terminal object, also known in sets as singleton set, and this is what it is, X to the power of 0. And for example, in Scala 1, the terminal object is type unit. So in Scala, you in the category of types of Scala. So unit is a terminal object in that category. X plus 1, it's a union of objects, or a sum, a disjoint sum of objects. X with object X, a union of object X with object Y. In sets, it's just a disjoint union. In Scala, you can model it by using either. 0 is a notation for an initial object. Empty set in set theory. In Scala, it's nothing. You can also use null for that, but no. Okay, 0, initial object, nothing. So more notation. F is an arrow from X to Y. In Scala, they're all called functions or method, and I denote it the same way. In case of sets, we're talking about functions, and you're pretty much familiar with it, I guess. Arity of a function is the number of functions parameters. So if you have a function f from x, y, z to t, so this function in Scala, well, this is a notation in Scala. This function has arity 3. If we have a function f column t, so in a sense, it's a function. It has arity 0. It always returns a value of t, and it doesn't need any parameter. So this is more or less Scala notation for parameterized types. And people don't use it frequently in category theory, but I use it in category theory all the time. This means that we apply a P may be a functor, to a type, object, or set X. So what is P? could be anything, any mapping of objects. Like, for example, list in Scala. So list is the functor, X is the type, and we apply list to type X, and we produce another type. So it's list is an end functor in this case. And this notation is pronounced in Latin as quod erat demonstrandum, and it's also called tombstone, halmos, end of proof. So that's where proofs are ended in math theorems. So, and this is its notation. So, okay, done with notation. So what is a theory? Let's start with algebraic theory without axioms. By the way, there are two kinds of theories, algebraic and geometric. I'm not going to talk about geometric theories, just keep in mind, geometric theories are also out there, and they're very different from algebraic theories, so we're not going there. And algebraic theory, currently also known as Lawvere theory. Lawvere is a great mathematician in somewhere like Albany, New York, I believe. So an algebraic theory, T, consists of just one data type and a collection of operation symbols of finite arity. Finite is important. So here's an example, numbers with addition and multiplication. So we have zero arity symbols, 0 and 1. And for example, an expression in that algebraic theory is like this, 1 + 1, whatever. We insert parentheses, although they're not parts of the language, but they're like, I would say, parts of meta language. We probably have to change the word meta to something less proprietary these days, starting today. So another example, sets, algebraic theory of sets. We have algebraic theory, meaning like not the full set theory. We have union, intersection, singleton set, like given a set, produce a singleton set with just that element. And zero arity operation, this is used for empty sets. Here's an expression in that theory. So we take like singleton, united with this and intersect with this. If you know what it is, the result would be a singleton containing a singleton containing empty set. We don't care about results. This is a theory. This is not a calculation. So we don't say that this is equal to something. We cannot say that something is equal to something if we don't have axioms and we don't know how to transform something from to something else. And there's a word for a theory, algebraic or not, without axiom. The word is language. So because this is a language of expressions, that's all we can do, produce expressions. Any well-formed expression, well-formed means like we use operation symbols properly, we use the correct arity, and we just build a correct expression. And we can use BNF. Anybody knows what BNF is? Beckers-Nor form to specify the theory, because it's just expressions. So, but again, no axioms, right? A more complicated kind of theory, algebraic theory, the theory with axioms. So algebraic theory consists of one data type and collection operation symbols and axioms. And what are axioms? In algebraic theory, in geometric theory, they look different. Axioms look like this. We have an expression on the left, expression on the right, and equality symbol. This means that one expression can be replaced in another if we're doing something with like bigger expressions. Here's an example of algebraic theory of numbers. We have numbers, like we don't know what numbers are, but we have operations plus, multiplication, we have 0, we have 1, and have all these things like commutativity, neutral element for addition, neutral element for multiplication, and so on. I'm not going deep into numbers. We'll get there a little bit later with monoids. So another algebraic theory with axioms for sets. So we say that, oh, A union B intersection C is equal to A union B intersection A union C. So this equality, these axioms allow us to transform one expression into another and back. So here are examples of algebraic theories. Piano theory, we have one nullary operation, just number 0, like it's a symbol 0, and unary operation S. So the only expressions we can build is see a parenthesis is missing, right? Okay, anyway, you see that a parenthesis is missing. It should be SSS0. We could as well ignore the parenthesis. So that's all the correct expression we can have in piano, except that this one is not correct. So magma with root. Magma is basically like a tree or like a monoid, but what does it have? It has a nullary operation called root, and it's denoted like this, like bottom, and binary operation, let's call it M. And here's an example of correct expression in magma. So M takes two parameters, so one parameter is bottom, the other one is this big expression. This big expression is M, and it takes two parameters, like M bottom, bottom, and then bottom. So here's an example of correct expression in magma. Well, at least this one is correct, this one is not. Okay, but see, no axioms, so we don't transform anything to anything. Here's a nicer example of an algebraic theory, monoid. I believe there are at least two talks that mentioned monoids today, maybe more. So Dean, no, not Dean. Bill definitely mentioned monoids and somebody else too. So what we have in monoids? We have a single type. We have a nullary operation, let's call it 0. And we have a binary operation, let's call it op. And two axioms. One is 0 is a neutral element for operation. So 0 operated with any A gives us A, and vice versa. So A operated with 0 will be A. And op is also associative. Not every operation is associative, but this one is, if we are talking about monoids, it should be associative. So A of B of C is A of B of C. So that's a monoid. That's an algebraic theory of monoid. It's not a monoid. It's a theory. We don't have any monoids yet. We don't know what 0 is. We don't know what op is. So we don't have monoids. All we have is a theory. Now, how can we have any monoids? We need models. So here I'll be talking mostly about models in sets, but actually you can take like any category where we have Cartesian product and union. So a model of a theory is just a representation of a theory, like given theory T, in sets, or maybe like in a category that we choose. So what do we need for this? We need an object X. So that object X could be a set, could be a type in a programming language. And for that set, we need these things. For every operation called M of arity N, we need a function that is an arrow. Well, an arrow is a function in set theory. It's just an arrow in types in programming languages. Maybe it's also called method, whatever. But so Fm is from x to the power of n to x. So it's an n-ary operation M. And given an operation M, we produce a function. So that's it if we don't have any axioms. But if we have axioms, those axioms should hold. I show you the examples later. So instead, well, see, we have like a collection of axioms. And again, did they say that there should be a finite number of operation symbols? Definitely a finite number, because arity is finite. You cannot have an infinite number of operations with a finite arity. No, we can. But again, it's finite, finitary theory. That's what I'm talking about. So if the theory has axioms, so axioms should be there, but if not, then okay. Instead of individual functions, like from x to the power of n to x, we can build a union. For all operations of arity k, we take x to the power of k and take the union, because for every such x to the power of k, there is an arrow to x. There will be an arrow from the union p to the power of t to x. So why do I denote it like this? Because it's basically a functor. It's a functor that produces these expressions, like primitive expressions of type x. And the whole collection of arrows gives us a function, an arrow from p to the power of t or x to x. So we could either have a collection of these or just build the thing and talk about the thing. That's it. Here are examples. Piano numbers. What do we have in piano? We have zero operation, nullary, and we have unary operation s. So do we need for this x to the power of 0, which is 1, and x to the power of 1, which is x. So this functor pt of pt is just a union of two possible powers, power of 0 and power of 1. So 1 plus x. This is the functor for piano numbers. Looks a little bit like option functor, right? So magma with root. So magma has what? Magma has zero arity symbol and symbol m of like arity 2. So we'll need 1 plus x to the power of 1 plus x squared. So this is how this, well, I would call it functor, that this is how the functor looks like, but we don't know if it's a functor. We can prove it separately later. Monoid. We have 1 plus x squared. Why? We have a nullary operation and binary operation, but we also need axioms. So this p should satisfy some axioms because these functions should be satisfying the axioms. So here's how it looks. In Scala, because it's 1 plus x squared, in Scala we can model it like this, either of unit and xx. So that's how this algebraic expression can be written in Scala. And we will need this operation from p to the power of x to 1 plus x to x, right? This operation consists of two operations. One is defined on one operation is called u, and the other operation is defined on x squared. So I denote it like this because it's it reminds the operations on matrices and vectors and so on. And we have a union, so that's how it is. So we have an operation that on the first component it's u, and the second component is it's m. And that's not enough because we need axioms, right? So here are the axioms written in severely categorical style. So this is the simpler version of the axiom unit. So we have x, map it to x cross x. So we apply u on the left side. The left component would be u, the component would be u, the right component would be the same x, so identity. So it's u cross x. And then apply composition, apply this merge operation.
Vlad, sorry, we've got a little problem here. We are offline now. We need a couple of minutes to solve it.
So when should I should
2
go back?
minutes.
Say again. Tell me to which slide should I go back? I don't hear you.
I can hear him. Can you hear me, Cloud Admin?
I can hear you, yeah.
I think they are offline, so I don't know where they are. So
where did do you remember where we stopped?
I think only they know. I could see you. He's trying to send me a note. Let me see what I get back.
Okay, you're live now.
But and does he need to go back a few slides, or does he?
Okay, I can go back a few slides. So, like this one, algebraic theory. Somebody should tell me like where I should restart.
Cloud Admin, do you know how far we should go back?
Is somebody around there?
I'm afraid we do not know exactly what slide was the last one.
Tell me which slide.
He doesn't know for sure, Vlad. So let's just go back 1 or 2 slides and continue.
Okay, so now a model of a theory. So given a theory, we can model it in sets or in any category with Cartesian products and addition. So what is a model? It's just a representation of theory T in sets or in a category that we choose. So what do we need for a representation of a theory? A theory, as we know, consists of just operational symbols, right? And we have one type. Because we have one type, we represent it as an arbitrary object, a set or a type in programming language. For every operation, we need a function. If the operation is called M, so we call the function fm. And if the operation is of arity n, the function is from x to the power of n to x. And if there are axioms, the axioms should be followed. I'll show you an illustration. Instead of individual functions, we can just take a union of all those x to the power of n for different n's, for different case, for all operations, and define the operation component-wise on this union. Let me show you the examples. Like one example, piano numbers, which has a nullary operation and a unary operation s. So we'll need x to the power of 0 and x to the power of 1, and take the sum. So 1 plus x. That's the functor for piano numbers. And a model would be an operation that maps 1 plus, a function that takes 1 plus x and maps it to x. So magma with root. If you remember what magma is, we have a root and we have a binary operation for gluing together parts of magma. So we have x squared for this binary operation, and we have x to the power of 0 for the root, for bottom. So that's the functor for magma with root. And monoid is like magma with root, but also it needs axioms. And I'll show you how we do it specifically for monoids. So a monoid is again 1 plus x squared. That's the type, the functor, right? So it can be modeled in Scala as either of unit and Cartesian product of x plus x and x. And we'll need an operation from P of x to x. And that operation consists of two components, u, that is defined on 1, and m, that is defined on x squared. And so denote it like this, as if we are dealing with matrices. And we will need axioms, associativity axiom and unit axiom. Associativity goes like this: take x cross x and apply m to the second and third component and keep the first one intact. So we'll have like from x, y, z, we'll have x, the pair x and m of y, z, and then apply m. So it will be m of x of m of y, z. So this way, and this should be the same as this. And this would be apply operation to x and y and keep z intact, and then apply operation to the result of that to z. So we'll have m of xy comma z. That's what we'll have, and the result should be the same. And the same with identity, like either we take an x, then take a pair x and unit and do a composition, or we take unit and x, so unit and x and take a composition, it will be the same identity on x. So that's how categorically we can express these axioms. So just an illustration. So now, to be like more abstract, go back a little bit. Here, P is built out of powers of x, and there can exist more than one operation of arity k. So there can be a union of several x's to the power of k. So this could be like a quotient, like 2x squared and 3x cubed and so on. So it looks like a polynomial. And here's a general definition of a polynomial functor. It's an end of functor because like it goes from the same category, from a category to itself, like for instance, from sets to sets. So a polynomial functor is a functor P that takes an object X and maps it to a polynomial object, which is the sum or union of Cn, which is a just integer number, no, natural number, multiplied by xn. So what's a natural number? It's just 1 plus 1 plus 1. So this is how polynomials look like. Polynomials, well, we don't use any negatives here in this specific case. So that's how polynomial functors look like. Here are examples of polynomial functors: 1 plus x squared, and anything. So if you don't see that it's a functor, you can it can be just an exercise, but it has a map, natural transformation that preserve identity and composition. So it's up to you to check. So an algebraic theory, any algebraic theory without axioms, when it's modeled by object X in a category C, or like by a set X, gives us a polynomial functor and an arrow from P of X to X. So it's just an algebra over the functor PT. And that's how algebras over functor are defined, like for any functor. It's an arrow from Px to X. So here the definition of algebra over a functor. So given a functor, an algebra over F is an arrow from Fx to X, right? So the category of all such algebras is denoted as C to the power of F. These arrows in this category are known as Structuresmorphisms in Haskell. So that's how it's written, like in a mixture of Scala or Haskell and categories. So if we have an algebra from F on X, an algebra on Y, the correct morphism, the structured morphism, would be an arrow from X to Y, such that this diagram can use. Okay, so what's a fixed point of a functor? A functor, a fixed point of a functor is any such object X that f of X is isomorphic to X. And a fixed point doesn't have to be unique, right? Suppose F is an identity functor, so anything is a fixed point. So the smallest fixed point of a functor is an initial object in the category of algebras. Here's an example. Like given an object a type A, list is a functor that is denoted as 1 plus A cross X. And the operation would be nullary and unary operation that multiplies by X. So this functor is an initial algebra because it's an initial object in the category of algebras. There's also the biggest possible fixed point, but it's a tricky thing. It's a terminal object in the category of F coalgebras, and it's denoted like this. And in the case of the category of the functor that multiplies by A, the terminal object is an infinite list, like in what? Well, stream in Scala, right? So why is this initial object a fixed point? Well, that's easy, right? So look how these algebras can be mapped to each other. So of course we can map this to this because f of I maps to I, and so f of y I maps to fi. But because it's initial, there is also a unique standard arrow from this to this. So this would be the same. So
yeah, Vlad, we are at time, unfortunately, and we have one more session after this. But this is beautiful stuff.
I need like a couple of minutes, okay? So this arrow is called the catamorphism, and I'll skip like existence of initial algebra, but it could be built multi-sorted algebraic theories. You can view the slides, it's complicated, and models, sample model, simplified model. So these are the topics worth studying further, like roles of terminal coalgebras, categories, parametric types, Lawvere theory in original formulation, by Lawvere, and counterexamples, like non-finitary monad doesn't have initial algebras. So this is the book where one chapter is dedicated to model theory. And this is a collection of links. One is basics like GADT and so on, basically by people that invented generalized algebraic data types. Andrei Bauer writes it pretty nicely. And Sergei Vinitsky also writes that stuff well. And these are deep foundations. So Algebraic Theory's book, the big book, Lawvere's publications, and so on. And you can also read that stuff in McLean and Murdoch, and you can try to read NCATLab. Eugenia Cheng also has a nice talk on that. And so that's it. I'll switch to config, and this is the link. Okay, thank you.